In this lecture, we construct an interesting and useful class of examples, which is the Grassmannian. Let our n be greater than 0 and k in the interval from 0 to n. We denote gkn, which is the dimension k linear subspaces of Kn. It is called the Grassmannian of k-planes in Kn. Our goal is to make the gkn into a variety. It is even a projective variety in a natural way. To make it clear, we need the algebraic concept of alternating tensor product. And we first give the definition of multilinear map. A k-fold multilinear map F from Vk called alternating if f v1 to vk is 0 for v1, v2, vk in the vector space V such that vi equals to vj for some I not equal to j. Then, for any permutation sigma, we obtain that f v sigma 1 v sigma k is the signature of sigma multiply f v1 to vk. Then we give the definition of alternating tensor product. Let V be a vector space over a field K. Then a k-fold alternating tensor product of V is a vector space T together with a map tau from Vk to T, and satisfying the universal property. For every k-fold alternating multilinear map Vk to W, there exists a unique map G from T to W such that the diagram commute. Such T exists and is unique, and we can take T to be the tensor product of V quotient by L, where L is generated by V1 tensor Vk for Vi equals some Vj for some I not equal to j. We write this T as like this, and tau of V1 Vk is V1 cup product V2 and cup product Vk. Next, we give some examples. Let V be a finite dimensional vector space and n be the dimension of V. E1 to En be a basis of V. In the same way as EI1 tensor EIK form a basis of ordinary k-fold tensor product, the alternating tensors EI1 product EIK for all I1, I2, Ik in ascending order form a basis of lambda kv. So we have the dimension of it is the combination number. Next example, we see that lambda 0 of V is the field K, and lambda 1 V is V, and the dimension of lambda nkn is 1. An important remark: if Vi in our vector space can be written under the basis Ej like this, then V1 cup product Vk can be written as a coefficient and the basis EI1 cup product EIK, and this is in ascending order. And the coefficient maximum minus of matrix whose rows are V1, V2, Vk. To realize our goal, we need a lemma. It is if V1, Vk in our vector space and W1, W2, Wk in vector space are both linearly independent, then V1 coproduct Vk and W1 coproduct Wk is linearly dependent in lambda k kn is equivalent to the span of V1 Vk equals to the span of W1 Wk. Then to realize our goal, which is GKN be a variety, we first show that GKN is a subset of projected space. We set if the map from GKN to this projected space be the Placer embedding. It sends an element span V1 to Vk in GKN to this. F is injective and well defined by the previous lemma. And for any k-dimensional linear subspace L, the coordinate of FL in the projective space are called the Placer coordinate of L. So Placer coordinate of L is the coordinate of FL in the projective space. Next example, we show the Placer embedding of G1n is simply a map from the linearly subspace, the span of this vector, to the coordinate in the projective space. Then we see that G1n is isomorphic to Pn-1. Next example, we see two-dimensional subspace L in G23. L is spanned by two vectors E1 plus E2, E1 plus E3, and the Placer embedding sends L to the coproduct of these two vectors, and it can be written like this. And the coefficient of FL is -1, 1, 1 in P2. So -1, 1, 1 are Placer coordinate FL. Alternatively, these are three maximum minors of the matrix 1, 1, 0, E, 0, 1, which means that the three maximum minors are this, and this. Note that a change of this spanning vector will perform row operation on this matrix, which change the maximum minors and most by a common constant factor. This shows that the homogeneous Placer coordinate of L are well defined. Next step, we show that the Grassmannian GKN is a closed subset in projective space, which means that the Grassmannian is indeed a projective variety. So we have to find suitable equations describing the alternating tensors in lambda kn such that it can be written as the so-called pure tensors. So our goal is to find equations describing the alternating tensors in this that can be written as pure tensors for some v1, v2, vk in the vector space Kn. And the key lemma is the following. For a fixed non-zero omega in lambda kkn with k less than n, we consider the k-linear map F is send a vector v in Kn to v product omega. Then the rank of F is no less than n minus k, and the equality holds if and only if omega is the pure vector. An example, we see that if omega is E1 product E2 in lambda 2k4, then F send the vector to this vector product E1 product E2, and we see easily that the rank of F is 2, which is exactly n minus k. And the corollary of this lemma is if F be a Placer embedding from GKN to the projective space, and then the Grassmannian is a closed subset of P n k minus 1. In particular, it is projective variety. And here's our proof. As GNN is just a single point, so we can assume that k is less than n. Then a point omega in the projective space P n k minus 1 lies in GKN if and only if omega is the class of this vector. By lemma, this is the case if and only if the F in the previous lemma send V to V product omega has rank F equals n minus k. As the rank of F is no less than n minus k, this condition can be checked by vanishing of all n minus k plus 1 times n minus k plus 1 minus of the matrix corresponding to F. But these minus are polynomials in the entries of this matrix, and thus in the coordinate of omega. So we can see that the condition for omega in GKN is closed. So indeed, we have proved that GKN is a closed subset of projective space and hence projective variety. An explicit example is given by G24, which embeds in P5. It is given by vanishing all 3 times 3 minus of 4 times 4 matrix of this map F, which means that it is a subset of P5 given by 16 cubic equations, since there are 16 3 times 3 minus of 4 times 4 matrix. And we will see later that a single quadratic equation suffices to cut out G24 from P5. Then we give an example to compute the dimension of GKN. We use the construction of a fine open cover of Grassmannian, and so we first show an alternative description of Grassmannian. That is, the Grassmannian is the space of all full rank K times n matrix modulo the row transformation. So this is the alternative description of Grassmannian. Let U0 be the affine open subset where E1 coproduct EK, the coordinate, is non-zero. Then a linear subspace L in the Grassmannian is in U0 if and only if it is the row span of K times n matrix. And the left side A is an invertible K times K matrix, while the right B is an arbitrary K times n minus K matrix. Multiply such matrix by A minus 1 at left does not change its row span, so we use that U0 is the image of this map. It sends A minus 1b to the row span of EK, see, where EK is elementary matrix. It is easy to show that F is bijective and also morphism. So U0 is isomorphic to this, is an affine space. The same argument also holds for other affine patches where one of the plical coordinate is not zero. We conclude that GKN can be covered by such affine spaces, which means that GKN is an irreducible variety of dimension K times n minus K. So the dimension of GKN is K times n minus K. This follows from the fact that if UI is an open cover of X and any intersection of two is not empty set with UI irreducible, then X irreducible. The next example, we take the full rank 1 times 2 matrices in reduced row form, and they are of the form of these two. Indeed, this is equivalent to the Grassmannian G12, and the 1 star corresponds to A1 in P1, and the 0, 1 corresponds to infinity point in P1. So we have G12 is indeed P1. The next example, we use the affine cover construction of Grassmannian to show the following property. We know that there is a really and well-defined set theoretic bijection F which sends an element in GKN to Gn minus Kn. It sends all k-dimensional subspace L of Kn to its orthogonal complement. It remains to show that F is a morphism. We do this on a affine coordinate. Let L be described as the subspace spanned by the rows of the matrix EK. And the matrix C as the affine coordinate of L. Note that we have this equation. So the orthogonal complement is the subspace spanned by the rows of this vector, this matrix. But the maximal minors of this matrix are polynomials in entrées of C, so F is a morphism. The next example, we show that G24 in P5 can be defined by a single equation. The homogeneous Placer coordinate of G24 in P5, we denote this by Xij for 1 less than I less than j less or equal to 4. Then we have G24 is defined by the vanishing set of this equation. The proof is as the following. For any omega in lambda 2k4, we can write omega like this. Then, from the previous lemma, omega is of the form V1 cut product V2 if and only if the map F from K4 to lambda 3K4 has rank equal to n minus k. So omega cut product omega is V1 cut product V2 cut product omega. It is of rank 0, so omega k product omega is 0. However, we have omega k product omega is this form. And it is just this. So we have shown that x is just cut out by the quadratic equation